Olá pessoal, sejam todos e todas muito bem-vindos e bem-vindas a mais um conteúdo do nosso Summit Firjan e Festival Futuros Possíveis 2020 da Casa Firjan. Eu sou a Karen de Souza, estou com vocês aqui nessa jornada que tem sido incrível. E olha só, a gente já falou de futuro, né? Nós já falamos de futuro, mas tem muita coisa acontecendo atualmente. Por exemplo, tem especialistas que estão desenvolvendo soluções baseadas na intersecção entre o design, a tecnologia e a biologia para criar produtos mais sustentáveis e funcionais. E aí, diante dessas inovações, vem sempre um questionamento, né? Será que a gente vai viver o fim das coisas ditas inanimadas? Então, para tentar responder a essa pergunta e muitas outras, a gente juntou o trabalho do arquiteto Christopher Maurer, que está desenvolvendo com a NASA uma arquitetura viva que possa crescer fora do planeta, junto com o trabalho da pesquisadora e diretora do MIT Civic Design, Yihyun Lim, e do Andrea Piccolo, que é diretor-geral do Think Tank Innovation by Design, que, entre outros projetos, eles lideram o desenvolvimento de um tênis que é responsivo. Esse tênis está sendo desenvolvido em parceria com a Puma. E para mediar essa conversa, a gente conta com a Karina Araújo, que é especialista de conteúdo da Casa Firjan. Gente, eu queria pedir que vocês continuassem enviando perguntas pelo chat, porque essas perguntas podem ser incorporadas a esse debate e fica tudo muito melhor quando você participa, viu? Com vocês, então, prédios que respiram e tênis responsivos. Como mudaremos a forma de fazer e usar as coisas?
Hi everybody, good afternoon. As Karen said, my name is Karina. I'm here from Casa Firjan. And I would like to welcome Yihyun, Andrea, and Chris. Thank you so much for being here with us. It's such a pleasure. I'm very excited to hear everything that you guys have to say. In this panel, we'll have a little bit of a different dynamic than we had in the other panels you've already seen in the summit so far. We're going to have two brief presentations, and then we are going to go and debate. So it's very important that you guys contribute with your questions in the chat. And to start off our conversation today, I'll give the floor to Yihyun and Andrea. Thank you so much. Are you guys hearing me? All
Yes,
right?
sir.
Yes.
Okay.
Thank you, Yoon, please.
Yes. Thank you. Thank you for having us here. So today I'm going to share with you a presentation on biodesign, and this is a collaborative project that we have done both at MIT Design Lab and also Innovation by Design, which Andrea will present following my presentation, of very interesting products that we have imagined using the tools of biofabrication, biodesign. A lot of these will be quite conceptual, and I would like to share some of the ideas that we were developing. And Andrea will discuss more about how, with Puma, they have been thinking about bringing this into a possible production, into a product that we can enjoy at home. So Puma, at MIT Design Lab, have been collaborating with Puma, and MIT Design Lab is a small multidisciplinary research lab at MIT, and we have been working with Puma over the past 3 years on the topic of adaptive dynamics. So under this topic, we were investigating, what it means to, let's say, embed electronics into shoes, from microsensors, actuators, motors, and such forth to improve a performance or to both sense and actuate. At the same time, we're also thinking about, in the material structure of, let's say, midsoles. So here we were investigating whether the different possible shapes of the cell structures of a material that we can actually create into a design aspect. And in this case, this is the aesthetic midsole project that we did, and now it's released into a product that you can purchase at Puma, which is a very, it provides a cushion sole that harnesses your ground forces and then helps it to really absorb back and then to improve the performance of runners. So under this topic, we have been looking at aesthetics as one of the possible ways of investigation. How can we maybe probably use jamming as a tool and both the technique to think about making granular modifications. Embedded electronics, of course, as you have seen, and pneumatics. Oh yes, embedded electronics here, pneumatics also as well. and shape-changing materials, as looking at how materials itself can maybe respond to heat or humidity, and those it can actuate and deform. And finally, looking at biodesign as a possible area of interesting ways of innovating the sportswear experience. So from these, we have, what I'll show you today is on the topic of biodesign. So how can we create adaptiveness? How can we bring digital and physical experiences, integrate those without boundaries? So the living and breathing in the future of the performance, this biodesign is really a practice of using living materials such as algae or bacteria to create products. And you probably have seen examples of, football jersey made of a silk of a spider, or, algae-based products or mycelium, using those to create both fabric and maybe brick. So there are many ways of integrating or using bacteria as a medium to create these. And so we were looking at this, how can we use biodesign bacteria as a medium to think about the future of dynamic sportswear? And microorganisms, that's not something new. It's probably, we consume this, right? We have bread, we have wine, and it's all really using yeast as an activator, and also algae that we see in the environment. So it's not something drastically different or something new that we're trying to bring in, but then trying to harness like what is around us and then bring that into a material that we can use. And when we were working on this project, we're not biotechnologists, we're not biologists, so we also had to educate ourselves to learn about what kind of bacteria is out there. As you are seeing in this slide, we broke down into 4 steps, thinking about what could be the possible growth media, something that can help the bacteria grow, nutrition, antibiotics, users, or something that can also stop the movement. What is the input? What are kind of bacteria? What is the design that we are going to create? What could be the design layer? And where can we embed these? And this is really the important part, because that's something that we as designers can really think. And then, of course, the application. What is the final application? What is the input? What is the output? What is the final, let's say, consumer or product experience that we are trying to create? So using these, we were, testing out with the different materials, working on different medium, from mesh to fabric to other things, brainstorming a lot with also other local startup that we have been working with, BioRealize. So they came in to help us to really bring their expert knowledge into to the space of design and innovation. And this was made possible, of course, through a biodesign prototyping platform, a really small prototyping tool that is easy to use even for non-biodesigners, or non-biologists. So we can quickly prototype these in small batches in our studio spaces without having the wet lab that would require to work with biology and bacteria. So this was done in partnership with BioRealize, as I mentioned, a startup that works in developing these prototyping platforms. And we have created these 4 experiments. So I would like to share the first 3 of these experiments, which is the deep learning insole, the breathing shoe, and adaptive packaging. So this is all around the areas of sportswear. So we were looking at the shoe insole itself, the outer of the shoe, and then the packaging of the shoe. First, the deep learning insole. And this was quite interesting. We were looking at how can we improve the performance of runners by learning about the needs of the performance before, let's say, before you actually feel the need. So in this case, as you see, the deep learning insole has the microcultures that monitor biochemical vitals. So vitals that could indicate possible fatigue. It would alert you before that you may be hitting your fatigue, let's say, threshold. So with this, it would sense your sweat and also the different signals within your sweat, and sense and then send back the signals to, in this case, we were imagining that this can be sent back to your phone and have it analyzed, and tells you both your possible performance level, as well as telling you that it's you need to maybe take action in taking more water or other electrolytes to help you to perform better. So in the second part of our project, we were looking at on the upper of the chute too, again, to think about performance and optimizing performance as well. So the breathing shoe concept is made out of the biodegradable material that is patterned with microorganisms. So the upper of the shoe.
Yihyun, I'm
Yes.
sorry, but are you sharing any slides? Because it's not showing for us here.
Yes. You should be seeing. Oh, you should be seeing all of. Wait, have you not been looking at my?
I'm sorry to interrupt you, but you said like as you're seeing in the slide, and we are not seeing the slide.
None of the slides.
No, I'm sorry.
Oh my goodness. So I had my screen shared as I was told to share my screen. I am very, so, okay.
Can we see if it...
You should be seeing my slides, right? No. Yes. So I hope...
Now we're seeing. Thank you.
Yes, so I hope you were able to see all of these slides with me while I was speaking. Yes, so I was explaining about both looking at the adaptive dynamics as a topic, some of the shoes that we're looking into, the structure of the shoe, as I mentioned, the aesthetic patterns that we have been developing to create these performative midsoles. And of course, as I mentioned earlier, some of these ideas have come out as a product. In this case, an aesthetic midsole that is really about optimizing performance. And again, I will quickly try to recap what I have mentioned. So in this case, we were working with different materials such as aesthetics, jamming, embedded electronics, pneumatics, shape-changing materials, and biodesign. So the adaptive through biodesign, as I mentioned, so the biodesign is really, about working with microbacteria to create products, and it's, and I will quickly go through some of the other slides here. So we were thinking about using microorganisms that are around us. So I hope now we have the visuals to accompany what I was trying to explain, both, in terms of wine or bread, using yeast, algae. Those are some of the sources of the bacteria that we were thinking with. Again, to break that down into different ways of thinking. So what is the growth media that will grow the bacteria that we're using? What would be the input? So it depends on what kind of final output that you want to generate. So we would look at possible bacteria sources to see what we would want to work with. Looking at the design media also, like what would be the actual, let's say, layer that we're going to put the bacteria on, and then also to think about the application. So what is a final output? And so again, some of the experiments that we did, working with materials, working with also another, brainstorming a lot about the possible actuations, outputs, inputs, and so forth, and also doing some quick testing and prototyping using the biodesign prototyping platform, which we have been working with BioRealize as our partner. So with these, we have created these 4 experiments, and I hope that you see my screen now. And yeah, so I will explain again. So these 4 experiments include the deep learning insole. So this time, I hope it makes better sense as you're seeing the videos too. So here, it's a disposable insole that you can insert into your shoe, and what it does is that the microbial layers that's embedded within the structure, it would detect the pH levels in your sweat. And what we were also playing with in this concept that we were developing here is that some of the vitals in your sweat can indicate your fatigue level, and we can hopefully monitor your performance level as well as your possible fatigue threshold level as well. And then it can give you both analysis of your performance as well as alert you to take preemptive action in whether taking more electrolytes, water, or taking a break, so you can really optimize and maximize your performance. So the second shoe, I think we caught up. So the breathing shoe is another concept that we moved up to the shoe, and then we were experimenting how can we embed bacteria on the upper of the shoe. So it would be a mesh with the cavity pattern, which then the cavities are filled with bacteria. And again, the food, we call it gelatinous media, that the bacteria will start to eat away. And what's interesting here is that you would start with this black blank shoe, and over time, as you wear the shoe, your very specific heat pattern by how your foot would generate heat from your sweat, it would activate the bacteria, and then the bacteria will start to eat and try to grow. So it would eat away the growth medium that is embedded into the layers, and then you would have this custom pattern of the shoe. So here we were thinking both personalizing your own shoe in terms of creating custom patterns, as well as hopefully creating your own ventilation pattern so that you can have more air coming from the parts that you need the most. And the adaptive packaging is then we moved to the outside of the shoe and thinking about how can we create a packaging that can be adaptive. So in this example, we were using yeast as the input. And here, to simply put, this biodegradable plastic, the outer material has both the bacteria and the growth medium. So imagine that you can feed, you can have the growth of the yeast to grow up to, let's say, 1 week, 3 months, or 6 months, or however long that you want to keep it. So you would feed it up to that amount. And then afterwards, and here in this case, you saw that, it was also heated up. So once it's under a heat lamp, it would heat up, the yeast would activate, form to the product that's inside. And then after it's been activated, it would start to eat and grow, and meaning it would start to eat away the growth medium, and then after that time that we have programmed it to live and sustain, it would then eat away the outside material and then biodegrade. So this was, we've called it programmable packaging. So you can use bacteria and really control the amount of food that you can give to create this customized packaging experience. So these the biodesign projects, we have exhibited these concepts during Design Week a few years back, and it was really interesting to engage with the public and really get to see what they were thinking, the responses from the public when we show this idea of using bacteria in their sportswear, their everyday shoes. And it was really about designing new experiences, right? And in our case, we were using our body as an interface. So whether it's our heat or the sweat level that we generate, so our body can become both the controller, and also then using microorganisms to sense and both actuate. So you wouldn't need specific batteries to keep it alive or to sustain it, but then we're using the kind of, we've called it digital by nature. So we're using nature to create these digital experiences that we are accustomed to. So digital by nature, again, this comes back up. And through that, we were exploring the idea of adaptive dynamics. And this was really kind of us to rethink and redefine the relationship that we currently have with products. So it is said that, every year, billions of sneakers are being produced. And I don't know how many pairs of shoes that you have at home or how many different colors that you have, or if you're a collector. But I think this kind of gives us a good chance to think about what does it mean? What kind of relationship do we have now with the products that we buy? Whether we just buy it, use it for a bit, and then dispose it, or can it be something that we can continue to have to cultivate the bacteria, treat it as a living material, living organism, and then to live through the cycle of bacteria too. So we wanted to pose a question of kind of rethinking the current product relationships that we have. So I'll stop here and then I'll toss the baton to Andrea, which he'll talk more about the one of the concepts that we further developed.
Thank you, Yun. Let me just share my screen. Okay, so thank you, Yun, for your presentation, very interesting. And what we did then was like understanding how to bring one of these concepts to a prototype, to a product prototype that we can think about to like then distribute and have available for like consumers on the market. So we started from this idea of biodesign. We took the breathing shoe and we evolved it from a concept to a prototype. And we presented to the public during the Design Week in Milano in 2019. I have here, so as part of a very big, let's say, public event that is held every year here in Italy. I have here a short video about our product. So the breathing shoe is a shoe that like evolves and adapts over time to the unique, let's say, ways in which the consumer like walk and run. It's of course unique to yourself and to the user because like the patterns that are created by the degradation of like the layer of biodegradable material that is paired with bacteria will create unique patterns that will improve like ventilation and air circulation within the food. And of course, embed this idea of the self-manufacturing that is very interesting because like the shoe comes with like a full layer of, let's say, biodegradable material that then is like evolving while is like used by the consumer itself. I want just to show you a very short video about like the perspective of Puma about that in the words of his head of innovation, Charles Johnson.
At Puma Innovation, much of the work that we do is in the space of adaptive dynamics, and that is creating products and technologies that adapt to the athlete's body or to their environment in which they're doing their sport or their activity. So biodesign is a really important space for us to be working in because for the first time, we're able to use bacteria to allow a product to adapt to the athlete and to customize it for their particular needs. With the breathing shoe, we have identified a way for the environment inside the shoe to be adapted for the user, not just for athletes, but for everyday consumers as well. Top scientists worked side by side with the best industrial designers to design and develop the material that's making bioevolution possible. Biodesign delivers on a completely new dimension, and that is self-manufacture. Because the shoe responds to the user participates in the last manufacturing step of the shoe. What is the most exciting for me is when we started thinking about biodesign, it was so unreal, so futuristic. It goes completely against convention. And so making that real really brings something new. And that's super exciting. We're taking a step into the future today.
So, how we did the challenge and approach this challenge to make an idea, a concept of breathing shoe to turn it into a prototype and a product. So the first thing we did, we partnered with the Fraunhofer Institute of Stuttgart to run some experiments about biodegradation. And of course, the experiments were about understanding and finding the right material to be used as a biodegradable material and to be used on the upper of the shoe. So we tested the Fraunhofer Institute tested different microorganisms, starting from starch and running from PCL, PLA, HB, so very different kind of materials. And here we can see some results of this biodegradation. And of course, this was very interesting because it allowed us to understand which were the best materials to be used and how to use that. Of course, then the second part of the experiment was to have an informed biodegradation. So we didn't want to have like a sort of random biodegradation, but we did need to have like more biodegradation in the areas where that were more exposed to like the movements and the heat and the sweat and the humidity of the food of the consumer. So we had to understand where these bacteria could be like more exposed. The idea was, of course, to really find like best patterns to really get into a product that could be usable, but also respondent to the like real uniqueness of each consumer like eating the map. So here we can see how in some experiments we ran of informed biodegradation, we had some more like biodegraded points and areas and materials. And what was interesting also for us to discover is that also like the shape and of each materials was really helping in like guiding and driving this biodegradation towards the results that we wanted to achieve. Here, for instance, we can see the degradation at different stages. It's quite clear on the image on the right side. So here we can see how over time the pattern emerges from the degradation of the whole. Like you see the lower part, we have a full like surface that is totally covered by biodegradable material, and you can see in the upper part how this material is degraded. And so this is how we applied this technology, and how looks like here in like a complete shoe after, where we can see here how the areas that are more exposed to heat and sweat are much more degraded than the other ones. And that for us was a very interesting way to like run from the concept to a prototype. Of course, then we had to show the results of these experiments somewhere, and we chose Milano as the right place, and we built an exhibition and that we curated. Of course, we presented the whole like experiments and the results of that experiment, but most important, we presented a prototype. That is the prototype that you have seen, like the runner was wearing in our first video. We produced 6 of these shoes, and some of them were used to make some, of course, promotional videos. Some of them are still there, and of course are very, very degraded. Just a focus on this last part of like the patterns that we use. We use these like reaction diffusion patterns that actually are functional, because the idea was to have like the maximize the surface of the textile and of like material to the exposure of bacteria and microorganisms. And then what happened is that we discovered also that these like functional patterns have also a very good like aesthetic and visual qualities. So then we kept them as part of the shoe, so as part of the real DNA of the appearance and the aesthetics of the shoe. And then the next step was to think about how to move from a shoe to other, like what was the next challenge. And the next challenge was about like not thinking only about shoe, but to the whole like clothes. And in 2020, we started a new project partnering with Puma, of course, Material, that is a company in Sweden, and Living Color, that is a company in the Netherlands. And we started applying this concept to also the clothes. And we can see here how like this pattern were used to like create the scaffolding of these cellulose clothes that is produced by stream material, and it's actually a total disposable cloth. The results of these new experiments and new approach can be seen online following this link in this like designpage.puma.com, where we are presenting the results of all these concepts applied to clothes and not only to a shoe. There is no time today to talk about this, but I think it's very interesting, and I really like recommend you to visit this website. And that's all from my side for today. Thank you.
Thank you so much. Thank you so much. So now we are going for Chris. Take the floor, please. We are eager to hear you.
You bet. Thank you. I'm so glad we got to see the slides. We talked about this earlier in the week, and I got to say my imagination was wondering, you know, exactly what this was going to look like, and it did not disappoint. It was a brilliant concept, and the visuals were just extremely beautiful. Okay, so we're moving from products to architecture. My name's Chris Maurer. I am an architect. I'm based in Cleveland, Ohio. And I'm struggling to switch slides. There we go. Okay, so we had we had a very good introduction into biomaterials. You may have seen from my first slide, I actually refer to them as bioterials, and that's a bit of a made-up word, but the reason being is that biomaterials, when you Google that, you get something like this, usually things that are used in medical applications. They're natural or synthetic materials, and we like to distinguish what I'm going to talk about today from those synthetic materials, just by removing a syllable from biomaterials. So we are talking about biomaterials, and the way that a way to think about them differently from bio-based materials which include wood and bamboo and adobe, and you know, even if you really think about it, plastics are bio-based because they come from fossil fuels. The difference between biomaterials and bio-based are that we define biomaterials as something that uses an organism's growth in the manufacture of the product. So we heard earlier about bacteria that actually produces products. On the left there you can see a rock that we physically made using bacteria to secrete calcite, and that bonds together aggregates like sand and rock the same way that cement does, but with a much smaller carbon footprint, and uses that natural organism instead of using cement. In the middle there you'll see fungi or fungal mycelium, which is used to bind together other sorts of constituents, usually bio-based in themselves, waste from agricultural processes or industrial processes. And then on the right, algal-based products that can actually use the growth of algae, which could either be plants or bacteria. to create products that are plastic substitutes that are more biodegradable and again are better for carbon sequestration, because you actually sequester carbon by growing algae. Here's another example that actually bridges a couple kingdoms. This is bacterial cellulose that comes from what's called a symbiotic culture of bacteria and yeast, which is abbreviated as SCOBY. If you drink kombucha, you're probably familiar with the SCOBY that is actually used to ferment the tea that you drink. But it could also be used to make parchment and leathers and different applications. What you see there on the bottom left is actually a Band-Aid that's used to treat burn victims. And it sounds strange to use bacteria to treat a medical ailment, but in this case, it's the bacteria is probiotic in the same way it is in your kombucha. There's a company in the U.S. that's looking to commercialize that idea of actually taking bacteria and secreting the calcite to bind the materials together. They're called Biomason, and that phenomenon is known as MICP, or microbial-induced calcite precipitation. That basically just means the bacteria produces the calcite that's used to bind together the materials. Some of our close collaborators at the Center for Bits and Atoms and Yihyun's colleagues at the Media Lab and MIT are working on producing 3D printing technology that can actually become fourth-dimensional in the fact that it uses time to let an organism to grow. So you can actually 3D print with a material that has embedded life forms in it, and over time those products change because of the embedded spores or bacteria that are used to grow over time. Lest you think that's hard, here are some of my younger interns working on the same process, and they're 4D printing, not with artificial intelligence like Filippos's that you saw before this, but with actual intelligence. But your results may vary depending on the precision of your instrumentation, and so I think probably going towards 3D printing technology is going to be the future of this, and in artificial technology where it's not maybe as smart as my children are, but is very adaptive and good at doing one thing over and over again, which Filippos has demonstrated there with his printing process that actually learns every time it makes a mistake, it's able to correct it in the future. So it's really interesting technology there. Mainly what I'm going to talk about is mycotexture, and this is using the growth of fungi to create materials. The two leaders in that technology is a company called Ecovative, based out of New York, that produces packaging materials, and a company called MycoWorks, based in California, that do leather materials or leather substitutes using the growth of mycelium to replace leather. And so it's a vegan substitute for that. And I think we'll hear more about that after our talk today. But broadly defining mycotexture, it's shaping the built environment using fungal mycelium. And just in case you're curious, mycelium is the vegetative form of fungi that consists of root-like branching hyphae. When you look at the images of mycelium, it's easy to see them as roots, but I usually try to dissuade people from that analogy, because if you were to compare the mushroom to the tree and the mycelium to the root, that's kind of a bad analogy. A better one is to compare the fruit of the tree to the mushroom and the mycelium to the tree. And in that case, it doesn't seem quite as crazy to think that you can build out of that, because we build out of trees, don't we? The process is as easy as what a mushroom cultivator would normally do to grow mushrooms. They take mycelium and they inoculate that into organic substrates, and these are usually byproducts of either agriculture or industry, and then it can be used to be put into any form to create any shape, really, the same way that you could fill a form with concrete and then release it later. Here's a kind of a rundown of some of the panels that we've made. More along the artistic side to some of these to show the process that basically, we've put it in this 2x8 frame there, and then used that to use various stencils to compact that to make artwork that you see here. Here are some scanning electron microscope images that actually show the distribution of this. So at a microscopic level, these organisms have are now bound with the substrates that they grew in. So it's really kind of a nanotechnology working for itself. These organisms bind at the cellular level and actually create a composite that's completely organic, but is still very thoroughly distributed. Some of the properties. So why do we look at this for architecture? It's one of the most multifunctional materials I've ever come across. It can be structural, it can be insulative, fire resistant, sound attenuating, and it has one of the smallest embodied carbon footprints of any material that I've come across. And so this is why I get excited about it. Part two, why bio? Well, we saw some really good examples earlier, but one thing to mention about bio is it's fast. So with these microorganisms, they grow a lot faster than, say, your macro trees and bamboo. You can actually get these materials to grow extremely fast and have products within weeks, rather than waiting for other organisms that might take years to grow, or decades sometimes. I mentioned nanotechnology. Why bio? Because it's small, and it's been doing nanotechnology for billions of years, in fact. And we can leverage a lot of those. I think we saw some extremely good examples with Yihyun's and Andrea's presentation about what they can do to be adaptive as well. I think that's one thing I'm going to add to this presentation, is to have that adaptive quality. Self-healing is a thing that bio does. So I do have some examples of that, where some of our materials have been destroyed at the same time as our steel forms when we put them in the press, and only our materials were able to heal themselves, not the steel. Bio can glow. That's just super cool. I think we'll put a pin in that, and we'll use that in the future. We don't really know how to leverage that exactly just yet, but that's something that I think the future is bright on, if you will. And very importantly, bio can create life from death. Here you see what fungi does. It actually converts dead matter into living matter and reinstates it into the into the biome in new ways. So that'll bring me to my first example of projects that we at Red House are working on, where we look to actually bring life from death with our biocycler. This is a project where we're actually taking construction and demolition waste and reconstituting it into new materials, using the same process that you saw earlier, where we talked about the cultivator actually just inoculating mycelium into the substrates. So we can get these woody, cellulose-rich substrates directly from waste material from the construction industry, and then create new products. One project that we're working on with NASA through their NIAC program is to develop concepts for self-growing structures for off-planet missions. And I'll talk a little bit about that later. And one that's really exciting that we're working with, again, MIT again, in the Standard Bank in Africa, is to create food job shelters and access to high-tech equipment, all in the same project with our biofab. And that's the first one I'm going to start with, where we are actually taking material that is waste from Namibia. Another thing that bio is really good at is circular economies. So there's a bush called the encroacher bush in Namibia that actually is choking wetlands, or choking the the aquifers, and so they're trying to get rid of that, and they've created a biomass industry around that. We can actually take that and turn that into food for feeding people locally, and also for export for creation of capital. And then we take the waste material from that and actually put that into low cost housing, or in some cases market rate housing as well. Here's a quick demonstration of how that works. We're basically growing mushrooms the same way any cultivator would. The mushrooms are harvested, and then the waste material from that is pressed into materials and turned into materials for construction. A few images of the progress on that. We're also using inflatable formwork to be reusable to create these structures. And the mushroom growing is well underway in Namibia, and we're in the process of building the first structure for this project. We've been able to create compressive strengths of close to 6,000 psi, which is fantastic for concrete, let alone a waste material from the agricultural industry. The second project I mentioned was that we're working with NASA. This is the NIAC project. We're working with the renowned astrobiologist Dr. Lynn Rothschild at NASA Ames Research Center. And this is a concept where we can actually take a small amount of material into space and convert it into, in some cases, thousands of tons of material just by adding water and carbon dioxide. There's 3 easy steps to this. First, you have to figure out how to get to Mars. 2, you figure out how to grow a house. And 3, just add water. And obviously, that's a little bit cheeky because it's those aren't extremely easy. But we've been going to Mars for decades now, so we know how to do that. We just don't know how to get people there. So a project like this that actually grows itself without the use of people is going to be something that NASA could really benefit from, because we don't need manned missions or crewed missions to make this happen. We can do this before any of the crewed missions go. It kind of looks like this, where there's a bag that's seeded with some of the organisms, and then by adding water and carbon dioxide to grow algae, you create the biomass needed to then release the mycelium to bond with that to create this composite material. One of the huge benefits of using bio in this climate is that you're able to leverage space radiation, which is the main liability for crewed missions off planet. The radiation is such that it's very dangerous for human beings to go into space, but we can actually use fungi and microbes that thrive in these conditions. So again, looking at turning a liability into an asset. The biocycler, I mentioned this briefly, and I'm going to kind of skip through a few of the slides. You already know the concept, which is basically turning construction waste into new materials. This is the first project that we're doing in an urban farm here in Cleveland, and we're just putting the finishing touches on this now, and it'll be delivered to site in next couple of weeks. Here are some slides of us actually building that, where we're taking construction waste, we're turning them into new materials, and then all of the waste sawdust and the chipped material that came from the process is being used to make the insulation material that goes inside. One more project, briefly, is where we're looking at taking algae and biomass using to sequester algae, which is a huge problem where I live here in Cleveland. This is Lake Erie that is suffering from a harmful algal bloom in this image. By taking that biomass from the lake and creating biostrips that actually sequester the phosphates and nitrates that cause the algal blooms, we create a model for actually dealing with the problem. We have to propose a marketable outlet for something before industry looks at things seriously to address these major problems. The pollution had been so bad in years past that the drinking water in some of the Ohio cities was completely poisoned, and folks were not able to drink it. Here you can see the combination of the mycelium and the algae growing together. So this is also to inform our NASA project, where we're looking at growing algal biomass off planet to create the substrate for materials. And we're also using prairie grass, and this is our biostrips. Another benefit of creating these biostrips, which you can see sort of towards the right there in that image, with large root systems, they can capture a lot of the runoff. They can reduce the nitrogen runoff by up to 80%, and the phosphate runoff, which is not only good for mitigating the harmful algal blooms, it's great for our farmers to actually keep those nutrients in their soil on their farm. It also helps produce pollinizers, basically bees and butterflies, around the edge of the farm. So even by losing some of the acreage of farmland, one study has shown that you can actually increase your yield just by having those insects that are attracted to the prairie grasses. And so in closing, basically, to sum up, not only are all these benefits to bio, it's a huge component in the circular economy. Here are 4 liabilities of our environment. One, the encroacher bush that is choking out wildlife habitat. 2, you can see there the emissions from radiation from our sun that is blocked on planet Earth by our magnetic shield, but once you get off Earth, it is not, and it becomes a super liability for our space travelers. On the bottom left, you see construction waste that can be turned into new materials, and on the bottom right are harmful algal blooms that can be turned into materials as well. These are all things that are considered a liability, but are not really addressed in any meaningful way until we can find ways of actually utilizing them in positive ways, and that's basically where bio can be extremely useful. So with that, I will turn it back to our...
Wow, amazing. Like as a product designer, I'm amazed and impressed, and I wanted to absorb everything you guys said. Since these 2 lectures were amazing, we passed a little bit on our time of it, so we'll have like a brief Q&A, very fast. We had a lot of interaction in the chat, so everybody's curious and want to know a little bit more. So I'll try to condense some of the questions that we received. The first one, I think it's a very central question. It's talking about scalability. Like how actually marketable are we in the scale of development? Are we able to put a shoe like this to sell anytime soon? And are we able to construct like buildings out of these materials right now? How do you guys see these time scale? Anyone?
Andrea, you're muted.
Yeah.
Okay, sorry. I would say that in terms of scalability, of course, there are chances to really bring these like concepts and prototypes to mass production. I'm not sure about the timing because, of course, like products like these, they entail like a very big shift and change in the way in which like products like shoes or like manufactured like in fashion are now really manufactured. So like the shift from like current like ways of production to new ones, that can be quite longer than expected. But the technology is there. I would say that the products that I shown you are doable and feasible, and it's just a matter of really scale the production. Right.
One more thing I would like to add. I think in the case of the breathing shoe that you saw in multiple phases, from concept to further testing and development. So the technology is there. I think another aspect that I would want to add is it's a different type of a product experience. It's not just going to the store and buying and you're done and you can just leave it in your shoe shelf, but you need to take care of it. You have to treat it like it's a pet. You have to feed it. You have to keep it in a certain condition. You may want to kind of stop the process if you have reached a level that you are like, or maybe you can restart the process by giving the growth medium again. So it's a different type of a product cycle experience, and from the consumer side. And so I think it will also require not just as from the industry side, just putting the product out there, but also educating the public, or talking to the public, exchanging ideas about what it means to have a living material in the products that you use, your shoes, your clothing, and so forth.
That's so. I didn't even thought about that, but that is really interesting, because it changes completely not only the way that we construct and design a product, but it also changes the way we consume it. Chris, and what about buildings? How are we in scalability?
So the projects that we're working on now are all demonstration projects. So they're kind of we're doing one at a time, but they're all designed to be scaled as time goes on. And if we look at the material inputs for those, I think what's important to know is that construction and demolition waste, there's about 500 million tons of waste that go to landfills every year. So as far as using that as an input, that's extremely scalable. The Acacia mellifera, or the encroacher bush that we're working to convert in Namibia into food and to building materials, there's hundreds of millions of tons of that as well available, and an almost inexhaustible resource. The harmful algal blooms that happen to our lake, and the ability to use prairie grasses that could mitigate that. These are huge material inputs as well. So I think from a material input standpoint, that this is ripe for scaling. We're just working on getting some of these formulas down, finding the right partners to make the jump scale happen. I think that the opportunities are there, and it looks very promising, actually.
We received a question from Maria that I thought it was very interesting. She asked if you guys ever encountered any legislation problems by using this type of materials. Like, you envision you have to regulate all of this somehow, and it probably will be different from country to country.
I assume that's a little bit more addressed towards building.
Yeah, I think so. Yeah.
Yeah, in that case, yes. So we, again, at the demonstration scale, we work closely with the local partners to verify that everything's done within code and done safely, and that we actually put the burden of proof on ourselves. We do a lot of material testing to prove that the materials are safe. As these are mostly demonstration projects and we're not doing manufacturing per se, we just do basically localized testing for those. If there were a manufacturer that was looking to make building materials out of this and to sell those on the market, then they would have to go through the battery of tests that any building material would have to go through. And there would be, honestly, a bit of an uphill battle to get code writers to accept those things. So that is one of the major challenges that materials like this would receive in architecture.
Really nice. So unfortunately, we are running out of our time. So I'm going to close with a very open question that came from Isabella. And she asked, how do you imagine the connection between technology and biology will develop in the future?
Can I use a pun and say it'll develop organically?
That's an amazing answer.
Yeah, I think with all the multifunctional characteristics that we're talking about here, especially with the adaptability that Yihyun and Andrea mentioned, that these are nearly inevitable just because of all of the positive attributes. The convergence will happen also with the limited resources that we have on this planet. I think we need to look at new ways of producing low carbon or carbon sequestering materials, and that is, I think, almost completely inevitable.
Right, and I also think with biotechnology, technology and design coming, converging into one, we can rethink the term that we have been using, smart something, smart product, and a lot of these, the smart terms have been associated with digital experiences, and I think we can start to expand that notion to include smart experience is not something only linked to digital sensors and digital networks, but it can also be enabled by nature. So I think there will be a lot more opportunities for design and some really interesting experiences that we can bring.
Andrea, would you like to put any consideration?
No, I totally agree with you. And I mean, there are a lot of opportunities, and looking into how this convergence will happen, it will be also very interesting and challenging for everyone. I think that the challenges we will have to face, and we are facing now as society, as people, will be always probably harder, and like all the contribution that we can find from different fields. So, and from the, let's say, the contamination of different perspectives, from science to humanities, and all the perspective can really bring value to new solutions that I think would be always more, let's say, complex in terms of development over time, but much more effective, I would say.
Okay, so that's what we can do for today. I'm very excited. I want to see how all of this is going to develop. I think it's revolutionary. I think it brings a lot of solutions to some of the problems that we've been seeing on our industry and our product production. So thank you so much for being here with us. It was amazing. And I don't know, everybody that is watching, I want to rewatch it all over again immediately so I can absorb a little bit more. Thank you so much.
Thank you.
Thank you.
Obrigado.
Thank you all.
Obrigado.
Bye. Então, pessoal, agora a gente vai para uma pausa com conteúdo. É uma pausa realidade aumentada na prática com o Thiago Toshio. E para entrar nela, vocês já sabem que já estão aqui, vocês vão fechar essa janela, voltar para o nosso hot site e clicar no próximo link. Daqui a um minutinho a gente já está de volta.